Every science has its parts where you just deal with unimaginable things. You know, you go to like chemistry and you have things like Avogadro's number, which is 6.02 times 10 to the 23rd. You can't imagine 10 to the 23rd of anything. Or physics has things like Planck's constant or these fields where you really can't see them, but you're supposed to understand that they're there. And the problem for each of these sciences is you get to these unimaginable states. Well, geology has one too. And that one is geologic time. Because geologic time, you just really, even though you think you could put time into some kind of context, it really doesn't work for geologic time. You know, you sit here and you look at the clock and say, oh God, when is this class going to end? And you know, you think, oh man, I'm going to have to sit here in this traffic jam for a whole hour. And time takes on this real small thing for us. But if we think about geologic time, we're talking about billions of years, 4.6 billion years that the planet was here. So geologic time is this unimaginable thing. You know, in fact, if you went through and did a little exercise where you said it put geology on a 24-hour clock, okay, the whole history of the Earth, 4.6 billion years, and started it at 12 midnight, and you said, okay, we start the Earth at 12 midnight, by the time oxygen shows up, you know, we get oxygen in the environment, it's like 11 a.m. By the time fossils show up, it's already in the evening, but by the time humans show up, it's 11:59 and 23 seconds. So you go almost through a 24-hour day putting it on there, and finally that's when humans show up. And we're talking about 4 million years of humans being here. So therefore, we're here, our little half hour, the length of this class, has nothing to do with reality of time, okay? And so therefore, when we talk about these events, you know, the cooling of a pluton or depositing of layers, these things took a long time to happen, millions of years, okay? And what we want to do then is we're going to put things into this time frame now, and we have three ways of looking at time frames geologically. Okay, and the first thing is what we call relative time. Okay, and relative time is who came first. Okay, how can you tell what happened first and what happened second and what happened third? We don't care how many years it took or how many years ago that was, but that's relative time. Okay, and so that's the first one. The second one is geologic time. Okay, and there's a geologic time scale, and that's based on the evolution of animals and what fossils you find in layers and things like that. That gives you a geologic time scale. Okay, and those all have names. There's Cambrian, Devonian, Ordovician, Silurian. These are all geologic names. Okay, and so those kind of give you time scale, and we'll see that in the book. In addition to that, we also have what is called absolute time. And absolute time is when you actually put numbers on things. So if it happened 5 million years ago, that's absolute time, being able to say 5 million years. Okay, and so what we're going to do is we're going to go through an exercise today, and you're going to kind of put time into context. We'll start with the relative time scale, and then we'll do the other two later. What we're going to do today is we're going to look at complicated geologic relations where you have things kind of cutting across and intruding and doing things like that, and you're going to figure out the history. So you're going to look at these things, and they're almost like a puzzle. So if you're good at puzzles, you'll be good at this. What you have to do is kind of take a couple of rules, and then we're going to apply them to situations, and you'll be able to interpret things. So for example, something complicated like this, where you have layers vertical and something underneath and something across there, maybe a fault on top of it, that is a complicated situation. But let's think about what kind of laws we can have to be able to tell what the order of things were to make this situation. Okay, well first off we start with a law called, or a group of laws called Steno's laws. Okay, and Steno came up with 3 laws that determined how sedimentary rocks could be laid down. Okay, and the first thing is we can start off with, we take some sediments and we dump them out onto the table, and we said, okay, they're going to be deposited like that, and we could say a few things about them. Okay, the first thing is they're flat. Okay, and gravity makes it that all sedimentary rocks are laid down flat. Okay, why did he say that in the first place? Obviously, he saw some rocks that weren't flat. So you have to go back and say, okay, they had to start out flat, and then you can do something else with them, tilt them or fold them or whatever. But they start out flat. Second thing is, even with this little pile that I've gotten here, you can see that you get maybe a thick section middle and it slowly thins its way off to the edge. There's no abrupt changes. You don't get any abrupt edges to your layers like you can see on this block. And that means that they have to have, in addition to this original horizontality, which is law 1, they also have a lateral continuity. In other words, they go for long distances before they disappear into nothing. Okay, they don't abruptly end. The last thing we have on this situation is if I'm going to lay down layers. So here, let's say that's a layer. I can lay another one on top, and another one on top, and another one on top. We can put those in a relative order. The bottom one has to be the oldest because I put that one down first. In order to put the other ones on top, the bottom one is the oldest, the top one is the youngest. That is called the law of superposition. It's like making a cake. You can't put the top layer on until you put the first layer on, then the second layer, then the third layer, unless, of course, you make an upside-down cake. Okay, so now we have rules for laying them down. So that's usually the first step. If you're going to do a geologic history, you have to start by putting the rocks in place. So that's deposition. Okay, so we deposit sedimentary rocks, or maybe we deposit volcanic rocks. But nonetheless, things have to be laid down to get our starting point. Then we look for what happens afterwards, either by changing the orientation of them, or cutting things across them, or lifting things out of them. Okay, and so that's the first step, though. First we put them down, then we can do things to them. So, for example, if we start off with a bunch of layers that are pretty much horizontal, the next thing we can do is we can tilt them. So, for example, going from this to this is tilting them. And so that has to happen after these are laid down flat. Then you can tilt them. Okay, so that is a stepwise progression. Or you might fold them. Okay, and so either we can take these and go to this. But these are things that have to happen after you're depositing them. So therefore, we can already start with a history. Deposition to get these stacked in order, 1, 2, 3. Tilting, that can be our second step. Or deposition, folding. That would be our second step after the deposition. A couple of other laws we'll look at are, one of them will be a law of inclusions. Okay, and inclusions basically means what was happened first. What rock had to be there first for the other one to be made. So, for example, if you find pieces of one rock inside of another, using to be made up as part of the other one, then you can tell that the pieces inside the rock had to be there first. Okay, and so therefore that's another law of inclusions that you can have. So, for example, if we look at this piece of conglomerate down here, you can see that there are fragments of rock in here. Okay, this made me bretcha, they're pretty angular. But here's pieces that are already in there. Therefore, that came from a pre-existing rock. The rock had to be there before it could be eroded down to make fragments to go in here. Okay, and so that's a law of inclusions. We could have the same thing in here if this bottom orange color is meant to represent a pluton. Okay, so that might be a granite pluton. Now, if there were pieces of this blue material inside of the pluton, these would be what we call xenoliths. And the xenoliths mean that the material that makes the xenoliths up had to have existed before the pluton came in. Otherwise, how would you get them in there? Okay, and so therefore, it's another one of these timing things. You have to have the rock there before you can take and put pieces inside of it. Another thing you can have is what's called cross-cutting relations. Okay, and cross-cutting relations then are, by looking at how things cross each other, you can tell which came first. So, for example, in here we have a pluton down underneath, as we said, which was maybe a granite pluton. The granite pluton, you can even see on the edge, the rocks here had to be there first for the granite to cross-cut those layers. So because it's crossing the layers, that means the granite came later than the colored layers. Okay, and so therefore that's a cross-cutting relation. We see the same thing if we look in here and see this dike that cuts through in brown. Notice that the dike cross-cuts all the other layers. We can look on top and you can see how it crosses those three layers there, and it crosses the granite. And so therefore the dike had to come after the layers, but also after the granite. Okay, now suppose I took this and I made a fault. Okay, so there's a reverse fault. Now you can see that even the dike is offset across this fault, and so therefore the fault cross-cuts the dike. And so by looking at how we cross-cut the different layers, we can then put together a history for this area. So let's figure out a history for this block here, this complicated situation. Well, we can kind of go through it by reconstructing it. And we said the first thing that has to happen is you have to put the rocks in place. So you have to have deposition to start. So we're going to deposit these three layers: red, yellow, blue. That's our deposition. Now we notice that in this rock, they're not like that anymore. They're not sitting on their side the same way this is. And so we have to have the second event after deposition is a tilting or some sort of event that would turn those things on end. And see, that's how we now can see it on end. So event 2 would be that tilting or flipping them up on end. After that, then, we now have this block then can turn into this by a couple of processes. First thing we have to do is intrude it with this granite. Okay, so now we have our third step is the intrusion of granite. Okay, next thing is the fourth step is we have to intrude that dike. Okay, so step 4 would be intrusion of the dike. Then the last step we might have is that fault. So step 5, in order to make this block like this, we have a 5-step process, or 5 steps to our history of relative history to make the area. Look at this block in here now. This is a very complex geologic area. It's got a huge number of units deposited and a huge number of cross-cutting relations. Let's go through and start by a step-by-step to try to get through that. This is the type of exercise that you will do in the lab today, where you will look at where there are numerous events that formed your block. Okay, so first we can take a look at, in the starting point, we come down here and you see that you deposit these different units, and we will assume they were all deposited in an order, so there are no unconformities between them. A, B, C, D, E, F, G. So we're depositing just sedimentary layers under the ocean, and you can see the water on top. The next thing we're going to have to do is we're going to first have to tilt the rock. Okay, and that's what takes these things that normally started out horizontal or flat, as we can see with Steno's laws. Then we're going to tilt the whole thing, and in tilting it, we're going to also cause erosion, because this will be an uplift type action. And also, finally, we put a fault in through there. So this second step, B here, really has 3 different things: uplift, erosion, tilting, and faulting all happen at the same time. Now you would, in your exercise, would list those all as 3 separate events. Now you can see in C has the erosion from the uplift, and we cut it all the way down until we have an erosional surface at the top of this intricate faulting and tilting section. Next thing we're going to do is go into deposition again. So we develop an angular unconformity on top of that tilted surface, and we then deposit J, K, L, and you can see we have cross-cutting relations then, in that the fault is cut off as well as the layers. The next thing that's going to happen is E, where we have an intrusion, the large intrusion, and that is labeled M on the big diagram, and you can see that comes in and cuts through all the layers that are previously there. Notice we also have erosion going on at the same time, and we see that then in letter F, where we have uplift and erosion. When we go down to letter G, we then can bring the the area back under the water and have deposition again underneath water, depositing units P and Q, and that means we have an unconformity, and this would be a regular disconformity between the J, K, and L units and the P and Q units. So there has to be, that's where you see that unconformity, however, no tilting in between. So after we have the erosion and then deposition in G, where we have P and Q deposit, we go down to the next step where we have an intrusion of letter R, and as you can see they also have erosion as well on the top. Okay, so we're eroding back the surface of Q, and then we go into the next step where we have S and T deposited. These are volcanic flows, so in fact we have a volcano going off that is causing that to happen, and finally we'll have erosion as the last step. After J deposition, where we put the T layer down, we then also cause erosion again. So you can see that this is a very multiple steps to get to this complex diagram. The other two topics covered in this chapter are also very important in geologic history, and these are the geologic timescale and absolute dating. Now, you will only be doing small exercises, if any, in this lab for this week. However, you are going to be covering fossils and geologic time in subsequent labs, and you'll be doing geologic dating within your lecture section, so you probably want to be able to take a look at these. This diagram here shows you the geologic timescale, and what's based on is the changes in life, in other words, evolution over time. And what you can see is these different periods given to you. Mostly these started off in eras with the Paleozoic era, the Mesozoic era, and the Cenozoic era. The Paleozoic era is mostly with invertebrate animals. The Mesozoic era is the age of reptiles, and the Cenozoic era is the age of mammals. Okay, so within them they have periods, and you can see you have the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, and Permian periods, all part of the Paleozoic era. These are broken down by changes in invertebrate animals, and you can see the pictures of the invertebrate animals here. The Mesozoic era has the Triassic, Jurassic, Cretaceous, yes, Jurassic Park. These are dinosaurs, okay, or the age of reptiles. And then the Tertiary and Quaternary are part of the Cenozoic, and these are mammals. There will be some exercises in subsequent labs where you'll be looking at the fossils and being able to say something about the time period from them. This next diagram shows the decay of a radioactive parent to a daughter element. And in this case, you can see all of the time periods that go by and how the decay takes place, starting from a newly formed mineral grain with a certain amount of radioactive element, as shown in these blue dots, and as it decays with time, the red dots, or the daughter product, will wind up replacing that blue parent. And so by looking at it, knowing how many red dots versus how many blue dots, and knowing the rate at which these things change, you can then get the exact age of the rock. Notice that the curve is not a straight line, and this is because these change in what is called half-lives. So instead of going at a constant rate of change, this is a half-life. It means that half of the parent decays to an equal amount of daughter. So you can imagine if you have 10 grams of parent, in one half-life it changes to 5 grams of parent to 5 grams of daughter. After 2 half-lives, which would be another hour or whatever else period of time, you would then take the 5 parents and drop it to 2.5 parents versus 7.5 daughters. And so therefore that's the way this breaks down, and that's the way you have the curve. This is a good diagram, not only for this lab but also for your lecture class.